Hey guys, welcome back. This is part two of our not quite 1, 2, 3 blocks. In the last video, we prepared and annealed the material, and now we're getting into squaring it. Now, this operation here, I'm just side milling the rounded edges off. We had to square it before so I could even put it in a vise. You'll see it's up on parallels now. Those half-inch square blocks are not integral to the vise. We may at one point go over that probably in a milling machine video. Now this is, you can see where I'm just working my way in. I'm trying to touch off the cutter. I don't want to really just ram into the material and take a heavy cut right off the bat. So you also see how that isn't an even width all the way across. Now that's because this chamfer isn't even, this was cut out of the center section of a spring and it tapers. So all of our faces are not even close to square, and we've really got to take our time making this square. At the time of recording, I have also ground the individual pieces square on 4 out of the 6 faces. We'll have to grind everything fully square on camera, but it's frankly pretty tedious and it doesn't look as exciting on camera as this does. There's not much of a smoke show, and when you're really tickling in parts, it's checking it on the surface plate, which we'll go through and I'll explain later in the video. Now, we're just hogging off material for this. I'm only showing one side. The other side looks exactly the same. It's not a terribly quick process. This machine is only 1 horsepower. And also you'll see how I'm always pushing the cutter into the fixed jaw of the vise, not the movable jaw. And that's because the fixed jaw doesn't deflect under load. That's much more rigid. So using the Y-axis on a vertical mill and pushing into the fixed jaw is how you get as much rigidity as you possibly can out of the machine. And I'm doing here what's called conventional milling, which is basically the cutter is rotating against the movement of travel on the machine, and the reason to do that is because you can't grab and pull, and there is some slop, especially in these older machines. So if you do what's called climb milling, where you move the cutter with the rotation of the machine, you can take up that backlash and break stuff, and that is not a good time. And as someone who does not enjoy broken things, I don't want to do that. We're also going to spare you the whole tedium of squaring blocks. There's a million videos on it, and after this step here, it does get kind of tedious, and it's just guess and check, guess and check. I think I do show face milling it because, frankly, face mills are kind of impressive, but I took a tooth out on it because this is really chewy stuff and I hit a hard spot. So instead of chasing it with a face mill and swapping inserts, I just ground that face because it was faster and everything was close enough to get through the slitting saw. And that's really what mattered. It doesn't need to be perfect all the time. Now we'll just cut here, we'll cut in approximately 30 seconds to the face mill, which is definitely an interesting tool. And this project is, I think, a good learning experience for YouTube, and not a bad learning experience for me. It's always good practice to really try and make things as square as possible. It's not usually what happens on the mills. I mostly use this for boring, not squaring. Now here we are. This bigger cutter I've switched to is 2 inches in diameter, and I think I've already touched it off, and this is just my finished pass, where you can see everything starts to shake because until the cutter is fully engaged in the material, there's so much space between flutes, you get a hammering effect. So you really have to give this very little feed to get started, and not a lot of feed overall, just so you don't break inserts, and it's not great for the machine either. You know, as a rule, try not to break stuff. Don't be a dum-dum. If you can avoid it, at least, you know, not everyone's perfect. And we'll pop this guy off, switch it out, and next shot. In the next shot, we will show you the slitting saw. No, that's also something that's really tough to film because it's kind of an awkward operation, and it is not necessarily easy to film because you either don't see anything because you are trying to stare through the part, or all you see is the saw turning. So here we are, I got the slitting saw set, and I already made a couple of passes just to touch the saw off before this. Now, I'm always really gentle in the beginning with these saws because it is not a good time. You can very easily break a tooth off. I didn't want the pressure being on camera. But after I establish my first 50 to 60 thousandths of an inch, I tend to give it progressively more and more feed into the material or depth of cut as we go, because there's two schools of thought on slitting saws, and one of them is take as much as you possibly can in each pass, and the other one is just take nibbles at it. Now, I waffle. I think you should start with nibbles because, in my experience, saws tend to deflect more as you're starting to load into the material. As you get a deeper and deeper depth of cut, the kerf actually starts to support it, and it can only deflect so much. So, as I said, I take a progressively deeper depth of cut as we go, and there's more support to the blade. Now, the larger diameter saws are relatively flexible. Small diameter saws are more rigid, and you can get a little more aggressive with them. However, we don't really need to get too aggressive on this. This is only a 1 horsepower mill, and with this arbor, I've actually sheared the key off with this saw. It's narrow and hard, and keys are soft. I'd rather the key fail than the cutter, because the keys are really inexpensive to replace, at least relative to a cutter. And, you know, I got a lot of these. I like to use them, and I like to use oil on them like it's free, because these are tough to resharpen, and I've actually had these heat up, bind, and then break, and a shattered slitting saw is not a good time. But I think this here should be my last pass all the way through the material, and I just leave a little bit. You'll see here, yep, I do leave just a little bit, enough so that the part doesn't go shooting off. Also, this jack here, fighting with the camera, you know, we're experimenting with on-machine shoots now, but this jack here is just so the jaws don't twist on the vise. So you get a much better grip if this isn't, the jaws aren't kicking to one side or the other. And once this is cut, I took a quick shot of explaining how this setup works. It's really pretty simple. It's just not necessarily immediately obvious, and not the kind of thing you'd think of unless you've been doing this a lot. Yep, right here, we're just kind of very close to finishing the cut, and we can just break the part off by hand once we shut the machine off and get the saw cleared. You don't want to sneeze and stick your finger into that. That's a great way to spend way more money than you want to. So here we are, is just milling the two parts to the same height. I decided to do this instead of using taking another cut with a slitting saw. It's a little bit lower risk, and the things I have in between the vise jaws and the parts are called hold downs. Now they're Starrett model, I think 54C. They're a rather obscure tool. I don't really see them a lot, but you can see here I'm just tapping that part down because I felt it move a little bit as I was closing the vise and just wanted to double check. And I'm touching the cutter off now. The goal here is to have these about 60 or 80 thousandths of an inch oversized from 1 inch. So I have a lot of room for grinding and making everything square, and we hit that goal. I didn't give myself as much length as I wanted when I milled the ends to length, unfortunately. I did manage to get everything square without much trouble, which was stressful, but we made it work. Precision grinding can be tough at times. Now this really here is just hogging material off. We're tickling this one down to try and get rid of the sawn finish. And you'll see hog hogging material off the far part, the taller one, just to match heights. We do manage to get pretty close, I think, within a couple of thousandths, and that's one of the advantages to these hold downs, is because these two parts are never going to be the exact same width. There's always going to be some difference, and there's a bunch of different ways to do this. I just wanted to do it all in one setup, which was cool. It actually worked. I wouldn't really recommend doing this. I think it's slower than it would be if you just put everything up on parallels, measured the height of the lower one, and milled off a prescribed amount, because you could take bigger cuts that way. These hold downs don't hold that well. The part does move a little bit, and it's one of the reasons I gave myself so much extra room, is just in case that did happen. Now, it's just, this is, again, like I said, when you're removing material and you want to do it quick, always into the fixed jaw. I think in this setup it doesn't matter, and you can see this lard oil burns a lot. Works great though. The surface finish for what it was fantastic, which was a pleasant surprise actually. I wasn't really prepared to get this good of a finish on such a chewy material with a repeatedly resharpened end mill. Do sharpen all the end mills on my surface grinder. Cutting the gash for chip clearance is really tough, so I never seem to get as good a finish with them as I do with factory end mills, but even the cheapest of the cheap carbide end mills are like $35 to $70. When you start getting into the really boutique ones, you can be looking at a couple $100. So I get moderately inexpensive ones and just resharpen them until they're little nubbinses, because we don't have the horsepower on this machine to really take much side milling. So you're kind of forced to take a relatively heavy width of cut, but a shallow depth of cut. And you can see here, I'm experimenting with really light cuts, and I sort of play around with it as we go through this part with, do I take a little bit at a higher feed? What feels the best? What's giving me the best chips? And I think what I settled on was like a 50 to 80 thousandth step over, and I believe this was about a 200 and something thousandths, 250 thousandths depth of cut off the top of my head. Looking at it, I think it's actually quite a lot more than that. I think we're closer to 350 thousandths, because you can see that step on there is about 2/3 the width or 3/4 of the width of the end mill. That's pretty respectable in alloy steel for a 1 horsepower step pulley. I think this would be a fantastic removal rate on a lot of those benchtop mills. I know what's funny to me too is watching, I think particularly Blondie Hacks, her videos where she's cutting and talking about, wow, I'm thrilled, I get a 50 thousandth depth of cut. That is less than I can do in the x-axis on this machine, and the y-axis is a lot more rigid. On the y-axis, frankly, you run out of horsepower before you run out of rigidity, at least with an end mill this small. So it is funny watching how different people's perspectives are just based on the machine they use. And you'll talk to guys who run newer machines than this or nicer machines. The stuff I am struggling with, really pushing the machine, and that is the absolute limit of what I can do. Newer stuff will do without a grunt. The 3 horsepower variable speed Acers are pretty good machines. They don't seem to last like the old Bridgeports did, but get what you pay for. You can do a lot more work in an hour on one of those. It pretty much there with a 1/2-inch end mill, you can just bury the whole thing and go. On this, I couldn't even consider that, because what I'm trying to balance here is you want at least a 2 or 3 thousandths of an inch chip minimum, so that you're not rubbing and heating up. So counterintuitively, a heavier depth of cut might run cooler than a lighter depth of cut, because you're able to push more heat into the chip and there's less rubbing, so you actually rub against the base material just that much less. And these parts were fairly cool after I finished this operation. I could handle them with my bare hands without much trouble. But as this video is running relatively long, we're going to cover grinding in the next part, so part 3. And grinding is much slower paced, and it's much more about sitting on a surface plate and taking your time. So we'll compare squareness and parallelism on these two guys, and then we go to the surface grinder. And the surface grinder is an order of magnitude more precise than a milling machine, and it's also your heat control really, really, really starts to matter. So on a mill, because of how precise you can work, it's not a big deal if everything warms up at the end, because that thermal expansion isn't really necessarily going to be relevant for your degrees of precision. But on the grinder, I can just leave the wheel off the part, let it run for 30 seconds or a minute, and then come back at my same depth of cut, and I won't even touch the part, because just a couple 10,000ths of an inch of movement in the part and the spindle is enough that the parts are no longer in contact. So when you're grinding, it's all about heat control. It's heat control and cleanliness. Cleanliness is next to godliness. You know, what you can get away with on a milling machine or a lathe, you really can't on a grinder. And you know, it's a little bit fun. You do get to work more slowly. It's much more about your setups. You know, you can't wing it on the grinder. Your repeatability just isn't there. For certain operations, you can take it on and off the mag chuck, but not always. So thanks for watching, guys. I hope you enjoyed this video as much as I did recording and editing it. So